So the final inhibitor type that we're going to talk about here are mixed mode inhibitors. This is when you have characteristics of both a competitive inhibitor and an uncompetitive inhibitor. So you have affinity for both the free enzyme and the enzyme substrate complex. And again, we get a complex looking Michaelis-Menten equation. Mixed inhibitors affect both Km and Vmax, and we'll talk about how that works here in a second in terms of the plot, both the double reciprocal plot and the Michaelis-Menten plot. And I want to mention another case that we're going to talk about here that's very uncommon, but for non-competitive inhibitors, not uncompetitive. We already talked about those. This is non-competitive in a different case. This is a special case of mixed mode inhibitors where alpha equals alpha prime. This is rarely seen. And here what we see is a decrease in Vmax, but the Km remains unchanged. Okay? Up here with a regular traditional mixed mode inhibitor, our Vmax is going to decrease and our Km is going to increase as well. So again, kind of an effect that you see from an uncompetitive inhibitor and a competitive inhibitor. Okay, so what are we talking about here? In this case, we've got both affinity for the free enzyme, which again can be competed away by increasing amounts of substrate to a certain, this part of it can. And here we've got affinity for enzyme substrate complex as well. Okay, typical mixed mode inhibitor. So here we've got our enzyme with an active site. Substrate can bind and either open up an allosteric site for our uncompetitive type of our mixed mode inhibitor, or it can interact directly at the active site. Okay, so we've got characteristics here of both of these types that we've talked about already. So here when we've got two different kinds of inhibition here. So alpha is greater than alpha prime in this case. So we've got higher affinity for the active site than for the allosteric site. Okay, we're going to see a decrease in Vmax, and in this case the Km is actually going to shift to the right as well. Okay, so decrease Km, but in this case the Vmax is shifting to the right. It's not staying. It's not decreasing like we saw previously with the uncompetitive inhibition. And if we look at this again in the double reciprocal plot, the Lineweaver-Burke, then we see kind of an interesting trend here, in that again we get intersecting lines. Okay, and Vmax has decreased, so 1 over Vmax increases, but now also our Km is getting bigger, so minus 1 over Km is getting smaller. So what we get is intersecting lines, but they're intersecting in this negative quadrant. Okay, we're not intersecting right on this x-axis like we saw before, and we're not seeing parallel lines. Okay, so intersecting right on the x-axis, that's competitive inhibition. Parallel lines in the Lineweaver-Burke plot gives us uncompetitive inhibition, and if we're intersecting in this negative quadrant here, then that gives us mixed mode inhibition. And the very final case that we're going to talk about here again is this mixed mode inhibition, where we have the same kinds of business going on here with competition for the active site or an allosteric site that's opened upon substrate binding. But this is a special case where the inhibitor has equal affinity for enzyme, free enzyme, or enzyme substrate complex. So in this case we call this a non-competitive inhibitor. Okay, so if we plot these out, what's not completely apparent from these plots, and it's hard to determine on this initial velocity versus substrate plots, is that the Km here is exactly the same. So Vmax decreases, but Km stays exactly the same for this specific type of mixed mode inhibition called non-competitive. It's a little bit easier to see here. In fact, it's a lot easier to see in the Lineweaver-Burke plot. Okay, again, when we plot these out, and we're adding higher concentration of inhibitor here, then we get intersection, but right on the x-axis this time, because our Km value hasn't changed. Okay, our Vmax is decreased, so 1 over Vmax increases here again, and our Km hasn't changed. So we get intersection right on that x axis. Now, of course, all these data are from idealized data sets that I've plotted all of these. And real data, it's a little harder to be confident about what kind of mechanism you're getting. You have to do your best and have some kind of chemical intuition about the system that you're dealing with in some cases. In other cases, it's pretty obvious what kind of mechanism you have. Okay, but this is material that you just takes some practice getting used to plotting out, drawing sketches, understanding what's going on, thinking about the mechanism and what's happening in each of these cases.